Section 4.4 is logarithmic functions. We talk about in math how to do things and then how to undo them. So in the past two sections, we've talked about how to exponentiate, and today we talk about how to unexponentiate. Just like you learn to add and then you learn to subtract, you learn to multiply, then you learn to unmultiply, divide. Well, taking logarithms have everything to do with unexponentiating. So here's the definition of a logarithm. For all real numbers y and all positive numbers a and x, where a is not equal to 1, this notation y equals log base a of y means that a to the y, I think I said the wrong thing here, y equals log base a of x if and only if x equals a to the y. Now when you look at that definition, just plug some numbers into it and it makes sense. I taught my girls logarithms while I was still tucking them in by saying, okay, if log base 3 of 9 means the exponent of 3 that gives you 9, what would that exponent have to be? If log base 3 of 9 means the exponent of 3 which gives you 9, the exponent of 3 which gives you 9 is 2. So log base 3 of 9 equals 2. All right, that's all logarithms mean. So if you can put aside any fear you have of logarithms and just think of them as, well, for example, I could give you any fraction, you could change it to the equivalent decimal, or I could give you a decimal, you could change it to the equivalent fraction. Exponential notation and logarithmic form are just two different ways of writing the same thing, and you should practice until you can go back and forth between them as comfortably as you go back and forth between fractions and decimals, theoretically. All right, notice that we do have a few restrictions here. A and x both have to be positive numbers. We said in exponential form we're not going to use negative bases. That's why this base a needs to be positive. We don't have any restrictions on y in the exponential form. We don't have any restrictions on y in logarithmic form. But one of my notes down here deals with why we have an additional restriction on x. So let's see these. When you see y equals log base a of x, make sure you can read it. You don't want to read that y equals log with a little a down there. It's log base a of x, and it means y is the exponent of a, which gives you x. For example, 5 equals log base 3 of 243 means that 5 is the exponent of 3, which gives you 243. When you change a logarithm to exponential form, it's completely checkable. Sure enough, 3 to the 5th does give you 243. Number 2 has to do with the restriction on x. The restriction is that x has to be a positive number. That's because you can't take the log of 0 or a negative, because there's no power of a positive base that's going to give you a negative answer. We already have the restriction that the base has to be positive. So if we're raising a positive number to a power, there's no way we can get a negative. And therefore, you can't take the log of a negative. There's no such exponent. Neither can you take the log of 0. There's no exponent of a positive base that will give you 0. And then note number 3, in the expression y equals log base a of x, x is called the argument of the function. Without some expression for the argument, y equals log base a is meaningless. I added that third note because I have had in the past some students take y equals log base a of x and try to solve it for x by dividing both sides by log base a. In which case I go, oh, you really don't understand, do you? Because this is not held together by multiplication. And so you can't remove it by dividing. Not only is it not held together by multiplication, log base A by itself doesn't make any sense. You can't walk up, well, you can walk up, but it won't make any sense if you walk up to someone and say, what is log base 5? I'm waiting on you to say of something. Just like it wouldn't make any sense if I walked up to you and said, what's the square root of what? So it doesn't make sense just to say log base A without that argument. All right. Number 2 on page 293 says write as an equivalent statement in logarithmic form. Just change these exponential expressions to logarithmic form. 3 to the negative 4 equals 1 over 81. What would that be in logarithmic form? Log base what? That's the base and exponential form of what? All right, let's go back up here a second because you may not understand the definition yet. When you take this x equals a to the y and write it in logarithmic form, the log still has the same base as the exponential expression. So, that part's easy. In exponential form, y is the exponent because it's the number that's up in the air. In logarithmic form, y is always the number that log base a of x equals. The exponent's by itself. So when we convert this to logarithmic form, the exponent's by itself. Log base 3 of 1 over 81 equals negative 4. If you're in the kind of bad habit of writing your fractions that way, then yes, you definitely have to have the parentheses. If you type it in the calculator, log of 1 divided by 81, the calculator's just going to take the log of 1 and then divide that by 81. So these parentheses would be required. If you put that in as a fraction, and it depends on what calculator you have, I'd say to be safe, yeah, put that 1 over 81 in parentheses. All right, C part, C to the P equals D. This one's not checkable because we don't know what C, P, and D are. But in logarithmic form, what would that be? Log base. Oh, I went across, you went down. Log base C of D equals P, and that means P is the exponent of C, which gives you D. In the D part, that would be log base what? What you said a second ago, Eric. Log base 7 of what? 100p equals what? X. And in the E part, that would be log base what? 3 of P over F equals negative 2x. All right, what about going the other way? I've given you logarithmic expressions. Let's write them in exponential form. The A part, log base 3 of 81 equals 4, means what in exponential form? All right, 3 to the 4th equals 81. C part, log base V of W equals Q, means what? All right, V to the Q equals W. D part means and really that gives us a way of solving a logarithmic equation for x. If x is part of the argument, just change it to exponential form. Now it would be easy to solve for x. Add 1 to both sides and divide both sides by 2. We'll talk more about that later. The e part, what would that be in exponential form? Four to the 5 minus x equals p. There are two logs that occur so often in the natural sciences and in many, many business applications. Yes, ma'am. Uh-huh. It totally depends on what the directions say, and these directions just say write in exponential form. We are going to have some problems that say solve, but this one didn't. All right, there are two logarithms that occur so frequently that they have their own special names, log base 10 and log base e. Log base 10 is called a common logarithm. If you see log without a written base, that base is understood to be 10. Just like if you see an x without a coefficient, it's understood that the coefficient is 1. If you see x without an exponent, its exponent's understood to be 1. If you see log without a base, its base is understood to be 10. Log of x is just an abbreviation for log base 10 of x. Similarly, natural log of x is an abbreviation for log base e of x. And when you see that e again, you think, no big deal, it's about 2.7. But natural log of x is called, log base e of x is called the natural log, and it's abbreviated ln of x. Make sure you're not writing that. I have seen college algebra students write IN, and I'm trying to figure out what they mean. I've got it now. I mean, but on their papers 10 years ago, I was going, what are they writing? Why are they writing IN? All right, number 12, write these in logarithmic form. If I didn't know these two abbreviations, these two special base logarithms, in the C part of number 10, I would say log base 10 of 38z equals x. But now that I know I don't have to write that base 10, I can just say log of 38z equals x, and that means the same thing. In the D part, I could write natural log of, oops, I'm sorry, I was saying before I knew the abbreviation. I could write log base e of d equals 4, but the abbreviation for log base e is just natural log of d equals 4. So what would that e part be in logarithmic form? It's the exponent that's on a side by itself. So not natural log of 0.1t, but natural log of x plus 2 equals 0.1t. It's always the exponent that the log of something equals. All right, number 14, going the other way, log of x equals y plus 4. What would that be in exponential form? The base is understood to be what? 10. So in exponential form, what would that be? Yep. And what about the D part? Yep. And the E part? What is it, John? Natural log is log base. So in exponential form, that would be well, you could write that as log base E of t minus 5 equals 1.2. It's not wrong because natural log's just an abbreviation for this, but what we want to do is change it to exponential form. In exponential form, what's the base? Same thing the base is here. It's base E. E to the, that's the exponent, E to the 1.2 equals t minus 5. John, is there anything you need to ask me about that? Okay, I know how that feels. All right, number 16 says find the value of each expression, and we don't need a calculator for this. Remember that log base A of x just means the power of A, which gives you x, or the exponent of A, which gives you x. So number 16, log base 8 of 1, I just need to think, what's the exponent of 8? That would give me 1. 0. Because 8 to the 0 does give me 1. And what about the B part? Log base 9 of 9. What's the exponent of 9 that gives me 9? 1. Because 9 to the first gives me 9. Matt, how about log base 5 of 0? Your forehead's doing the right thing. There's no such creature. There's no such exponent. There's no exponent of 5 that gives us 0. What's the other time that we've encountered no such thing? A negative under a square root, but imaginary numbers using eyes pretty much solve that problem. What? Because if I say, what's the number that you multiply times 0 to get 5, you're going to go, there is no number you multiply by 0 to get 5. And so what do you write? Undefined, you write the same thing for a logarithm that doesn't exist. It's undefined. Because, let's see how I can write that. 5 to the anything doesn't equal 0. D part, you have to squint hard on that one. Log base 6 of 6 to the 7th. What is the exponent of 6 that would give me 6 to the 7th? Yeah. If I say, what's the exponent of 8? No, let's see. What's the exponent of 8 that will give me 8 to the 10th? It's just what? 10. What's the exponent of, I'm trying to fall back on my ducks and pigs and it's not working so well. Log base anything of that same base to a power is just the power. I don't even know what to write for a because there. Because 6 to the 7th equals 6 to the 7th. Or maybe just if you understand exponents. That won't go far in a formal proof class in graduate school, Kayla. All right. Oh, what about the E part? 5 to the log base 5 of 4. Log base 5 of 4 means the exponent of 5 that gives me 4. Can you squint hard enough to tell me the exponent of 5 that gives me 4? Well, I know there is such a number, but I can't get it in my head. It's less than 1 is all I can tell you. I don't know the exponent of 5 that gives me 4, but I do know if I raised 5 to that power, what would I get? Let me make up another one right here. What if I said 3 to the log base 3 of 27? What's log base 3 of 27? What is the exponent of 3 which gives me 27? That's 3. So what do I get if I raise 3 to that power? You told me this exponent equals 3. So 3 to the third gives me 27. 3 to the log base 3 undo each other, just like log base 6 of 6 to the 7th undo each other. I'm just saying, I don't know what the exponent of 5 that gives me 4 is, but if I raise 5 to that power, it'll give me 4. F. All right, I'm going to make up another one until it clicks. What about 4 to the log base 4 of 16? This 4? No, this is an exponent and 4 is its base. Oh, so it was just a matter of reading it. It's 4 to the log base 4. So I'm saying on this problem, I can tell you what log base 4 of 16 is. What is it? 2. So if I raise 4 to that power, what am I going to get? I'm going to get 16. If you raise 4 to the power of 4 that gives you 16, it's going to give you 16. If you raise 5 to the power of 5 that gives you 4, whatever it is, it's going to give you 4. Be very careful with writing neatly it's always helpful in math, but especially with logarithms, you have to be able to see what's on the line, what's below the line, what's above the line. Your subscripts have to be clear and your exponents have to be clear. Otherwise, you're going to end up with expressions that don't make sense or expressions that are completely different than what the book intended. Okay, never mind. All right, the F part, log base 3 of 243, how am I supposed to figure that out? You mean 3? What power of 3 gives you 243? Just count by powers of 3 until you get to 243. 3 times 3 is 9, times another 3 is 27, times another 3 is 81, times another 3 is 243. So log base 3 of 243 equals 5. Actually, that was up in my note number 1. I didn't mean to use the same example twice, but I did. And then log base 2 of 128, same thing. Count by powers of 2 until you get to 128. Doesn't take as long as you might think. 2, 4, 8, 16, 32, 64, 128. 2 to the 7th equals 128. Log base 2 of 128 is 7. All right, make sure you understand what logarithms mean. Sometimes in math, you can kind of just do something by copying examples and not really get what it means. If you don't understand that logarithms and exponents are just two different ways of writing the same thing, exactly like fractions and decimals are two different ways of writing the same thing, you'll be confused about logarithmic functions the whole chapter. And this is something that folks struggle with in calculus. In calculus, you use a lot of logarithms. And so if you don't understand what logarithms represent, that's going to come back and bite you then too. All right, number 18. Ten to the log of 7. Yeah, that's just like the previous part E was. In number 16, when we had 5 to the log base 5, where is it? 5 to the log base 5 of 4, we said 5 to the log base 5, just undo each other and leave you the 4. The same thing is true in number 18, that's log base 10 of 7, and 10 to the log base 10, undo each other and just leave you the 7. In the B part, how about log of 10 to the negative 6? Do you understand why? Or yes, yes, because that base is understood to be 10, and log base anything with that same base to an exponent just leaves you the exponent. Ooh, I think 10 multiplied times itself 10 times would be way bigger than that. How could you figure out the answer to the C part without using your calculator? Count by powers of 10, just like in the previous example, we counted by powers of 2. Count by powers of 10 until you get to 100,000. 10 to the first is 10. 10 squared is 100. Times another 10 would be 1,000. Times another 10 would be 10,000. Times another 10 would be 100,000. So log of 100,000 is 5 because 10 to the 5th equals 100,000. Letter B, let me show you the corresponding problem on number 16. That would be just like the D part. When we said log base 6 of 6, undo each other and just leave the 7. Do you understand that on this D part? This is the exact same thing. This is log base 10 of 10. See if I can get them both on there. This D part's just like that B part. So if you have log base anything of that same base to a power, log base anything of 10 to a power, just undo each other and leave you the power. All right, D part. Ooh, one thing I wanted to say about the C part. What do you notice about the answer to, it's the same as the number of zeros? If you raise 10 to any power, you're going to get a 1 with that number of zeros behind it. 10 to the 10th is going to be 1 with 10 zeros behind it. 10 to the 4th is 1 with 4 zeros behind it. Wonder if that will help us in the D part. Log of 0.0001. Let's see. What is the place value of that 1? What's the place value of that 1? Tenths, hundredths, thousandths, 10,000ths. That 1 is in the 10,000ths place. How many times do you have to multiply 10 times itself to get 10,000? 10, 100, 1,000, 10,000. 10 to the 4th would give you 10,000. What would give you 1 over 10,000? Just double check it. 10 to the negative 4 is 1 over 10 to the positive 4. 10, 100, 1,000, 10,000. 1 over 10,000, which is 0.0001. So when I'm taking log base 10 of something bigger than 1, I just count the zeros. But when I'm finding log base 10 of something less than 1, I could figure out a rule to memorize, but I just always check my answer, which is a better way for me than memorizing anyway. Whatever I memorize, I'll forget. Whatever makes sense, I can figure it back out. All right, E part, e to the natural log of 8. What's that? That's just 8 for the same reason that in the A part, 10 to the log base 10 of 7 is just 7. The 10 to the log base 10 undo each other, and in the E part, e to the natural log undo each other, or e to the log base e undo each other. What about F? Natural log of e to the 2/3? That's, yeah, because that's log base e of e to a power. And we've already figured out that log base anything of that same base to a power, they just undo each other and leave you the power. Well, you could always check it. If you said that was 6, then well, let me see if I'm following you. You said e to the 1 plus natural log of 5 is 6. That means if I raise e, let's see, what would that would mean that, ooh, that's hard for me to say. Why is that hard for me to say? that would mean that not quite 3 to the 6th power. No, that's not what it means. I'm having a hard time saying what that means. I know it's not right though. Tell me one more time how you got the 6. Yes. Oh, okay, I gotcha. So you're saying that. Can I just pull, is this expression equivalent to that left-hand side? No, it's not. Yeah, you just need to write it down and look at it. These two things are not the same. But I do need to rewrite this somehow as something that I need to write an equivalent expression. How could I rewrite that so that somehow for the e and the natural log to undo each other, e just has to be to the natural log of 5? I know that this is what I want. I just don't know how to get it. What could I do with the 1 so that I'd have something that's equivalent to the line above it? It's not an equation, so you can't subtract 1 from both sides. You don't have both sides. I'm thinking this is natural log of 5 plus something in the exponent. What operation causes you to add exponents? When do you add exponents? When you multiply two expressions with the same base, right? So if I could write this as multiplying two expressions with the same base, then I would add the exponents. What does this exponent need to be equivalent to the line above it? Yep. And then what is e to the natural log of 5? And e to the first? The best we can do is just write it e. So the trick there was figuring out how to write that left-hand side as an equivalent expression that had e to the natural log of 5 as part of it with that 1 out of the way. Well, since these are added and you add exponents when you multiply two expressions with the same base, write it that way. Write it as a product of two factors that are both base e. All right, 22 through 34 say solve. And let's see, there have been 2 times so far that we've solved equations. We haven't done anything illegal. We haven't made any mistakes, but still we came up with an answer that wouldn't check sometimes. Can you think of what those 2 scenarios are? When you raise both sides to an even power, like if you have square root of x equals -3, there's not going to be a solution to that. But if you square both sides, you're going to think x equals 9 is the answer, and it just doesn't check. What's the other time that we didn't do anything illegal, but we got an answer we couldn't use? I'm really not talking about anything on that page right now. I'm just trying to remember. There were 2 times that I didn't do anything illegal, didn't make a mistake, but I got an answer that I couldn't use. One of them, Sarah remembered, is when you raise both sides to an even power. What's that other time I could get an answer that I couldn't use? You know it has something to do with a 0, but it's not 0 to a power. It's when we clear out fractions, we have to make sure that our answer doesn't make the denominator 0. All right? Yeah, right. We have to make sure that the answer doesn't make the denominator 0. So those are the 2 times so far that we've had to check the answer. We should always check our answer when we're solving equations, but those 2 cases we had to because it was possible to come up with extraneous solutions. Well, now we're adding a 3rd thing to that list. When you solve a logarithmic equation, you have to check your answer because that's the 3rd time that you may get an extraneous solution. All right, 22, log base 3 of x plus 4 equals log base 3 of 1 minus x. How can log base 3 of one thing equal log base 3 of something else? How is that possible? Not the same x, but the same argument. If they're arguments of each other. If I said log base 3, well, the pigs and ducks just aren't working so well in logarithms. The only way this can be true is if x plus 4 gives you the same number as 1 minus x. So if you have 2 logarithms with the same base, then their arguments have to be equal to each other. In other words, just set the arguments equal to each other and solve for x. Now that's not, we didn't divide both sides by log. That wouldn't even make sense. We just said if you have 2 logarithms with the same base that equal each other, the only way that can happen is if their arguments equal each other. If we solve for x, we can find the value that makes that true. Add x to both sides and we get 2x. Subtract 4 from both sides and we get -3. So x equals -3 halves. Because you subtracted x from both sides instead of adding x to both sides. I think -3 halves is correct. If I can use it. I don't think I've made a mistake, but I have to check for extraneous solutions. Well, if I let x be -1.5, what is log base 3 of -1.5 plus 4? What's -1.5 plus 4? 2.5. And what's 1 minus -1.5? That's also 2.5. So both of those arguments end up being 2.5. You end up with log base 3 of 2.5 equals log base 3 of 2.5. And certainly that's a true statement. So x equals -1.5 is the solution. Which makes me wonder, how are we going to know when there's an extraneous solution? How do we know if we've come up with something we can't let x be? Well, what can the argument, I know what the denominator of a fraction can't be. It can't be 0. I know what I can't have under a square root, or I'm outside the realm of real numbers. I also know what I can't take the log of. Negative number or 0. I can't take the log of a negative number or 0. Now that doesn't mean I can get never get a negative answer. Well, I got a negative answer right here and it checked. Log base 3 of 2.5 does equal log base 3 of 2.5. What I cannot allow to happen, maybe I'll make a note right here. X cannot make the argument. The argument is the thing you're taking the log of, and x can't make the argument less than or equal to 0. That's different than saying x can't be negative. X can be negative, the argument can't be negative, and the argument can't be 0. All right, so number 24, same thing. Log base 7 equals x minus 5, or not, I said that wrong. Log base 7 of x minus 5 equals log base 7 of 6x. Well, the only way that can be true is if x minus 5 is the same thing as 6x. And the only way that's true is if negative 5 equals 5x. And the only way that that's true is if x equals negative 1. But what makes that argument negative? Yes, it does. I didn't even notice that. If it makes either one negative, then you can't use it. Certainly, if it makes both negative, you can't use it. Makes argument negative. And so what do we write when we had one possible solution and we can't use it? Huh? No, well, x equals negative 1 is extraneous, but if I come up to you and say, what makes this equation true, which is what I'm saying when I say solve, what makes this equation true? Your head did the right thing, Sarah. There was only one huh? Yeah, that's it. There was only one possible thing that was going to make it true, and I can't use that. So if you say, what makes that true? I'm going to say nothing, or no solution. There's no such number. There's nothing that's going to make that true. Yes, ma'am. Arguments. Not unless you've made a mistake, because that's how you got the answer, by setting those equal to each other. All right, number 26. How do you think we'll solve natural log of x squared equals natural log of 12 minus x? They already have the same base. They're both base, what? E? So it's not the bases that we set equal to each other. They already are. It's the arguments you set equal to each other. X squared equals x minus, or 12 minus x. What is different about that equation and the equation we got in the two previous problems? Which makes it what kind of equation? Quadratic. How do I solve a quadratic equation? Nope. But before that, I have to. All right. X squared plus x minus 12 equals 0. X plus 4 times x minus 3 equals 0. X equals negative 4 or positive 3. Can I use both of those answers? Yeah. Nobody said I couldn't have a negative answer. If I put negative 4 in place of both x's, I'm going to have natural log of 16 equals natural log of 16. And that's true. I'm just going to write down something real quickly on the last three, and then I want to graph very fast. Number 30, I can't use the same principle I've used on the previous three because I don't have logs on both sides. But I can change it to exponential form. 4 to the negative 3 halves equals x. And then all I have to do is evaluate 4 to the negative 3/2. Take the reciprocal, the square root, and then cube it. If you don't know where 1/8 came from, hang around a minute after class. Number 32, same thing. I can't just, I don't have logs on the same I don't have logs on both sides, but I can do what? Change it to exponential form, realizing that log means log base 10. And that doesn't look like a subscript. It looks like it's on the next line. But what Kayla said is right. 10 to the negative 4 equals x squared. This is a quadratic equation. You can take the square root of both sides because you don't have a first degree term. X equals 10 to the negative 2, but what did I forget? When you take the square root of both sides of an equation, plus or minus, can I use both the positive and negative 10 to the negative 2? If I square it, what am I going to get? A positive, a square, a negative, I'm going to get a positive, and I can take log of positive 0.01 or log of negative 0.01 squared. Write it down and we'll talk about it. Hang around a minute, Kayla. All right, 34, e to the negative x. I have the same, or I have a similar problem in number 34 that I did up here in the e part, where I had to rewrite that expression so that the e and the natural log were together, and I could just say they undo each other. Number 34, I can't say the e and the natural log of x undo each other until I get that negative coefficient out of the way. A lot of times what you have to do in pre-calculus and calculus is write down what you want to have and then figure out how to make that happen. That's what I want to have, but where could I put the negative so that this left-hand side would still be equivalent to that left-hand side? Well, the difference here is this was addition, so I could take it apart as a product. The exponent had addition in it, so I could take that apart as a product. But this exponent doesn't have addition in it. That's -1 times natural log of x. What causes you to multiply exponents? There is something that causes you to multiply x. When you raise a power to a power, does that tell you how I could rewrite that left-hand side? Is that equivalent to the line above it? Yes, it is. Write down what you want and then figure out how to make it happen. Most importantly, check. Raise a power to a power, you multiply them. Sure enough, that gives me back what I started with. And what is e to the natural log of x? That's just x. So x to the -1 equals, I'm going to write that as 1/5 because that's what 0.2 is. There's more than one way to solve this, but that seemed the easiest. If x to the -1 equals 1/5, then x has to be 5. It checks. 5 to the negative 1 does equal 1/5. Say it one more time, John. Why did I have to do what? No, I didn't raise the left-hand side to the negative 1. I rewrote the left-hand side. I didn't do anything to it other than just rewrite it. Okay, that's important to understand. I didn't do anything to it. I just rewrote it as something that looked different but actually was the same. Because this was something to the negative 1. This negative 1's an exponent, that negative 1's an exponent. Say that one more time, Sarah. Natural log of x was an exponent. X itself wasn't an exponent. All right. We are officially out of time, but let me ask you something. Since I'm giving you Thursday to work on the practice test, can you give me 5 minutes of graphing down at the bottom of this? All right. 56, all I'm going to say is just change those to exponential form and punch them on the calculator. If log base x equals 1.8965, then in exponential form, that would be base what? 10 to the 1.8965 equals x. So just punch that on the calculator and you do the same thing with the C and the F parts.